row 3 and row 2 minus, or excuse me, row 2 plus 1 over 40 row 3, right? And so that gives us 1, 0, 0, 0, 1, 0, 0, 0, minus 40. See what I did? I mean, that changes this minus 40 into a dividing by a 40 makes that a minus 1. This becomes a minus 7/40. Oops, that's fine. Minus 7/40. 1/40. One minus 1/5. I'm sorry, just say 1 minus 8/40. Probably better for you guys. I think 8/40 is 1/5, right? I'll put some dividers in here. Try to keep me honest. Top row, we've got 1, that 1 minus 42 over 40. 0 plus 6 over 40, right? So many 40s. Let's see here. And then what we got? We got 0 minus 8 times 6, 48 over 40. And of course, this one is minus 7, 1, 8. I haven't done anything to it yet. Let's see your finishing blow. Row 3 divided by minus 40. And I'll try to clean up those fractions now. So what's 1 minus 42 over 40? Tell you what, I'm just going to call it, there's a 1/40th out front, yeah? So we can save ourselves a bunch of 40s. What's 1? 1 is 40/40, right? So 40 minus 42/40 is minus 2. 6, that was easier. Minus 48. Minus 7. 1. 40 minus 8. 32. Minus 7/18. Now that, my friends, is a inverse. Dare I check it? I'm a little nervous. Nah, we made a mistake. Oh yeah, we definitely made a mistake because this, if you just take the first column, right, and multiply it by that, we should get E1. I mean, we should get 1, right? This times this. I mean, it shouldn't give us 1. What should it give us? It should give us 40. Because then 40 over 40 should give me 1. Because remember, A times A inverse is supposed to be equal to 1 stuff. And if you multiply that, I get minus 2. I get minus 2. Oh, look at that, though. I get minus 2, minus 42. That feels like it should be a positive 7. maybe that's supposed to be a positive. Could this be a positive set?
Because you divided row 3 by negative 1, and it was a negative 7.
Yes. All right. This is characteristic of my calculation. My own particular way of making errors is my signature trademark to make the error in the last step. And so that is what I did, yes. Now, some of you have other, customary ways you make errors, but my own personal signature is to rob victory. Rob defeat from the jaws of victory, or whatever you say. I mean, you Patriots fans, you understand, but that's your, sorry. Obligatory. I watch one sports game a year, so I am allowed the joke. All right. Where was I? Oh, yes. So that at least fixes that, because then I've got the minus 2 plus 42, which gives me 40 over 40, which is 1. That's good. Is that everything, though? I mean, I still need that this dotted with that is 0. So that gives me like minus 14, minus 56, plus 70. That's 0, yeah.
In the last step, should the 8 be positive? Because in the one before it, I think it should be negative.
Did I drop a minus? Oh, yes, thank you. Right. So, what's the moral of the story here? I mean, even if you have the right computational idea, it's important to check your work at the end. And maybe with this kind of calculation, don't just give up on everything you did. Like, try to locate your errors rather than starting from scratch on something like this, I think. Or you might just not have time. I mean, it depends on the problem. Anyway, this is a not atypical test question. I can tell a lot from a question like this in terms of whether you guys have studied or not. If you've studied, this doesn't kill you. It's just kind of like, oh, this. I've done this before, but it's annoying. If you've never done this before, and the first time you greet it is on the test, it will crush you. You will not be able to get through this. It is just awful. There are very few people who can just like look at this and go, I should make the inverse that. Such creatures exist, but they're kind of rare. I may have expunged it from my notes, but I used to have a formula for the 3x3 inverse. Like you can write we write the 1 over AD minus BC, DA minus B minus C, right? That's the formula for ABCD inverse. There is a corresponding formula for the 3x3 matrix, but it's much more horrible, and no one insists that you learn this. I mean, I once taught a student linear algebra over the summer, and I told him in no uncertain terms, I'm like, you don't memorize this. This is just, out of curiosity, the formula for the 3x3. Then, like, I'm grading his, he did some, like, practice tests. And so I'm, like, looking at it. I'm like, how do you find this inverse? And then I'm like, oh, he memorized the formula. The one thing I told him not to do. So annoying. But anyway, a particular student, he knows who he is. Min. But, anyway, do you guys have other questions about homework? Oh, yes.
On problem 30, what does it look like for S be a subset of span?
So those, okay, so to see if S is a subset of the span of T,
Yes.
what you want to do there is you just want to look at the reduced row echelon form. The question is, what is the reduced row echelon form of T with S like this? And the reason you want to do that, if you calculate that, right? This equals whatever it is, you can, like I think I said you can use technology to do that, right? So use technology to do that, and then use the column correspondence property to see if there are any linear dependence, right? Like, for example, if the pattern ended up being something like, suppose, I mean, I don't know how it works out, but suppose the pattern ended up being like this. 1, 1, 2, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0. And that was the part for t. And then the part for s ended up being something like 1, 1, 0, 0, and then 1, like that. Right. So where again I'm using the notation that the matrix of S is just the vectors in S strung out into a matrix. If the row reduction worked out to that, what would that say? So suppose that T is T1, T2, T3, just for the sake of discussion. Suppose that S is S1, S2, for the sake of discussion. Suppose that the row reduction worked like that. What would that tell you then? What it would tell me is that S1 is equal to T1 plus T3. Does that make sense, you guys? I mean, I'm using the column correspondence property. This fourth column is the pivot column plus the other pivot column. See that? So going back to, what those mean, T1, T3, that gives us S1. In contrast, how about S2? Can I build S2 from pivot columns found in the T part? No. So if the calculation worked out like this, it would say that S2 is not an element of the span of T.
So S would be a subset if both of its columns had a linear correspondence with T?
Right.
Okay.
Yes. And by the way, for what it's worth, for my pet hypothetical example here, T is a linearly dependent set because the second one can be obtained as twice the first one. Yeah.
Could you just explain how S1 equals T1 plus T3?
I'm using the column correspondence property, the linear correspondence, which is just to look here and to see this column, right? It's equal to this one plus that one.
Okay.
Add this to that, we get that.
Okay.
And then so the column correspondence property says that that same pattern must also be present in the original matrix over here before the row reduction, like ignoring that.
Okay.
And that is that T1 plus T3 is equal to S1. Now the other thing that I've asked you in the homework, which is actually like pretty difficult, more difficult I think than I at first realized, and it looks simple. I asked you to write span as a set of equations. So let me just show you. I won't be able to get all the way through it, but let me just set one up. All right. Suppose I wanted to take the span of, say, 1, 1, 1, 1, 1, 1, 2, 3, 4, 5, all right? And suppose I wanted to write that as a set of equations. Suppose I wanted to say that that was the solution set to some set of equations. How would I do that? Well, here's one way I could do it. I could say, well, what I'm trying to do is I'm trying to say A times 1, 1, 1, 1, 1, plus B times 1, 2, 3, 4, 5 is equal to x1, x2, x3, x4, x5, right? So the goal here is find system of equations and x1, x2, x5, whose solution set is W. So I'm calling this thing W. But all you have to do is to look at this, right? And just eliminate A and B. Don't try to do it by hand. I mean, you could try. Try if you want. But I would highly advise that you write down the corresponding, like, you know, augmented coefficient matrix A, B, x1, x2, x3, x4, x5, you know. And it's a homogeneous system, so you got zeros over here, which I'll write just for the sake of. So for my made-up problem, which is actually harder than your homework, okay? You know, what does this give us? This gives us like A plus B, A plus 2B, A plus 3B, A plus 4B, A plus 5B. And so what is my columns here? I've got 1, 1, minus 1, 0, 0, 0, 0. 1, 2, 0, minus 1, 0, 0, 0. 1, 3, 0, 0, minus 1, 0, 0. 1, 4, 0, 0, 0, minus 1, 0. 1, 5, 0, 0, 0, 0, minus 1. You end up with like an identity, like minus the identity over here when you write it out. If you do row reduction on this, you can essentially ignore the top two rows. Those will be the A-B equations. And so like after you do row reduction, if you look at the final, for this one, if you look at the final 3 rows in the row reduction, those will correspond to the 3 Cartesian equations you need to get that span as a solution set. I gave you 2 4 vectors in 4-dimensional space, so you'll be able to just keep the bottom 2 rows in your problem, like problem 28. Or the 3-dimensional ones in like problem 29. I'm forgetting the numbers for the problems, but the other one, it's a little bit easier than that still. I'll try to say one more comment about this in class Friday because I want to help you guys out a little bit. This problem is harder than it first appears, I think. If you just try to do it directly, I had a lot of trouble with it personally. There's some ideas later we get geometrically that allow us to make it easier. For those of you in Calculus 3, the 3-dimensional problems you can use the cross product for if you want. But a lot of you guys don't have cross products, so I can't really expect that. All right, I shut up. Sorry I should have done this earlier. I'm not thinking clearly, obviously.